So let's look at ions. When anions form, it's because an atom gains electrons. So we're adding electrons to electron configurations. That's pretty straightforward. You just add some more in as if you were going on to the next element. When cations form, we lose electrons. And so then we have to take electrons away, but we have to make sure we're taking away the correct electrons. So we're losing them. They're being lost from the valence shell. For main group elements, it's pretty straightforward. You just go backwards from the order of filling. So here we have an aluminum atom, and 1s2, 2s2, 2p6, 3s2, 3p1. We've got 3 valence electrons here. And as we remove electrons to make positive ions, we're going to take off this 3p1 first, and then we're going to take one of the 3s electrons, and we're just take the other 3s electron. And so all 3 of those went away. They were lost to somebody else. And so now we have this electron configuration where we have this full S and P sublevels. So the atom for aluminum, there was 3s and 3p. And so we had 3 more electrons in there. And so removing the electrons, we're going to go get rid of this one first. And then this one. And then that one. Okay? Main group elements. For the transition metals, we're still removing valence electrons. It's just that this doesn't necessarily match up with the order of filling, because the 3d electrons got added after the 4s electrons, but the 4s electrons are the valence electrons. It's the people on top. Would tornado be a decent analogy for that? Except you guys don't know much about tornadoes, but tornado comes by and the tornado's going to take the top of the building off, right? And so here for iron, these 3d electrons, they're paying more for their room, they're higher in energy, but they are not valence electrons. They're not on the highest occupied level. The 4s are. And so the tornado is going to come by and it's going to take off the 4th floor and above and leave everything below. And yeah, tornadoes can do that. It's really, they can do all sorts of strange things. So we're not going to lose the 3d electrons. We're going to lose the 4s electrons, because those are the valence electrons. It has to be valence electrons.
So if we're going to highlight yellow, it would just be 4s.
Mm-hmm. So those are the valence electrons. Highest number, these are the principal quantum numbers, 1, 2, 3, 4, and we're back to 3 here, but 4 is bigger. So all the electrons in 4 something are valence electrons.
Okay. It's cheaper to fill the higher levels first sometimes, right?
Mm-hmm.
But
it's still further from the ground.
Right. Okay. So it might be you just have to go and collect all the highest numbers.
Mm-hmm.
Floor levels. Okay.
Yep. So it's going to lose its valence electrons first. So those 2 valence electrons go bye-bye. And we don't write 4s0 in here then. We just don't write it. So here we have 3p6 and then 3d6. And we've lost 2 electrons, so now we have a +2 charge in this cation. Now, if we're going to lose more electrons, now what are the valence electrons once we got rid of the 4s? Well, the 3s are valence electrons now. Okay? So we'll start at the end of the 3s and start working our way back. We're just going to lose 1 more, and so we're going to lose one of these 3d electrons. We'll end up with 3d5. So if we look down here, this is the orbital the orbital diagram for the 3+ ion. If we look at the it had 3 electrons in there. This is a valence shell because it's 4, right? So those get lost first. So that one and this one. And now now that's completely gone. I wasn't planning to do that, but it kind of worked out that way. And now this is part of the valence shell. And so now we're going to take an electron out of there.
And so the reason that we're continuing to the 3D is because that's the transition metal, so it's not going to like a nice safe big hole.
Yeah, so why are we taking 3 electrons and not just 2? Because, we're learning pattern, we just lose the valence electrons and you're done with it. But the valence electrons here are mixed up with the D, right? And the transition metals, many of these form more than one ion. Most of them form more than one ion. So how do I know that I'm supposed to take off 3 electrons here? Well, I'm trying to write the electron configuration for iron 3. I'd have to be told that, right? And this kind of helps us understand that, oh yeah, it's not so straightforward here. Aluminum's going to lose those 3 valence electrons, done, bang. But these guys, it's like, well, they're not all +2. And then there's the irregular electron configurations, like chromium and copper, where there's 1 electron in there, and then you get into the others, and it gets a bit complicated. Yeah.
When not electrons from like 3D, do you always start with
Yeah, so what you would do is you would take these off in the reverse order of filling. So when we filled these up, we put 1 spin up in every box, and then we started pairing up. And so when you're taking them off, you just reverse the process. So this would be the last one added. So last in, first out. Right? So the important thing is you first remove valence electrons, and with the transition metals, be careful that you're identifying the valence electrons correctly. After that, it's reverse order filling for everything. Magnetic properties of atoms and ions can be predicted. They are related to how many or whether there are any unpaired electrons in the orbital diagram. So unpaired electrons have a charge and they have a spin. They make their own little magnetic field, and then they get attracted to an outside magnetic field. In a diamagnetic atom, all of the electrons are paired up. So you have a spin up and a spin down paired together. And so those are not attracted to a magnetic field. They're actually slightly repelled, but we'll go with just not attracted. So paramagnetic has unpaired electrons and is attracted to a magnetic field. Diamagnetic atoms, all the electrons are paired and it's not attracted. This can be so confusing. I always have to stop and think about it. Okay, so we got paramagnetic, and we have diamagnetic. We have all paired and some unpaired. And we have to remember the correlation between these two things. My brain sees para and thinks pair, P-A-I-R. But that's not how it's spelled, and that's not what it means. So what I think about is di means 2. Para may sound like a pair, but di definitely means 2, right? And then I think of Noah's Ark. And all the animals went onto the ark 2 by 2, right? So diamagnetic, everybody's paired up 2 by 2. So diamagnetic corresponds to all paired up. And paramagnetic is the other. We have some that are unpaired. Because PARA does not have anything to do with PAIR. It means something else. Yeah. Question? So paramagnetic has unpaired. Diamagnetic, they're all paired up. Yeah. It is confusing. And then how do you remember, well, is it attracted or not attracted to a magnetic field? Well, you've got some unpaired electrons versus all paired up electrons. So this electron pair, you can kind of imagine how their spins are just going to be kind of together. They're paired up and they're just sort of like self-contained. And then we have this guy with unpaired electron, or more than one unpaired electron. And that guy looks lonely and like he might be attracted to a magnetic field, right? Because he wants to be with somebody. This guy, these are already with each other. They're already taken care of. If that helps, I don't know. Write the electron configuration and orbital diagram for each ion and predict whether each will be paramagnetic or diamagnetic. It is not impossible, but it is much more difficult to predict paramagnetic or diamagnetic from an electron configuration. So we definitely want to look at orbital diagrams here. And we can just look at the noble gas shorthand version. So for cobalt is in period 4, and so that's argon plus some. So there's argon in brackets, and then next is going to be 4s, and then there's some stuff going on in the 3D. And I find it helpful to write the atom first and then take electrons off, because otherwise I tend to do it wrong. So if we look at cobalt, the atom, how many electrons are there after argon? 9, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Because it can make a difference. If you take the wrong electrons off, you could end up with the wrong answer. So if I'm going to make a 2+ ion, I have to remove 2 electrons. Which ones do I take out? Yeah, take these out, because those are the valence electrons. So get rid of these guys. And then I can write my electron configuration, because it also asked for that. So that would be argon, 3d7, right? It's the electron configuration. And then it says predict whether it's paramagnetic or diamagnetic. Well, I look at these electrons, and I see we've got 3 unpaired electrons. These are 2 by 2, and then we've got some that are not. So this one's paramagnetic. It's hard to look at the electron configuration and see that, because to do that you have to visualize this anyway, so you might as well just write it down. Any questions about that one? Let's do nitrogen. It's not much of a shortcut, but helium. And then we've got 2s and 2p. And let's do the atom first. So for, using the periodic table, we can see there's 2 electrons over here, and then there's 1, 2, 3 electrons over here. That's the neutral atom. And then the 3 minus charge says I've added 3 electrons or taken away. Added. Right? We're adding negatives. So I'm going to add 3 more electrons. They're going to go 1, 2, 3. And then I can write the electron configuration for this ion. And then diamagnetic or paramagnetic, I'm going to look at the electrons and see, are they all paired up or are there some unpaired ones? They are all paired up, like the animals on Noah's Ark. They came in 2 by 2. Di means 2, diamagnetic. If you can talk yourself through that, hopefully you can do it quietly or in your head and not out loud during an exam. But if you can reason yourself through that, then you can come to the correct answer and not go back and be wishy-washy and change it to the wrong answer. And write it out on your paper if you have a hard time following it in your head, right? Any questions? Okay, now that we've talked about ions, what about the trend in ionic radius? Thankfully, much of this makes sense. So a cation is formed when you lose electrons, and so when you're taking electrons off the outside, you would expect that to make the thing smaller, right? And it does. What's a bit strange is how much smaller it makes it. So cations are much smaller. They're like half the size. And that has to do with removing the valence electrons, and now you're down into the next level, and so you've got fewer core electrons, and now you have higher effective nuclear charge, and so everything just goes and sucks in. So we look at like lithium here. Here's the atom has 152 picometer radius. The lithium plus 1 ion, 60. That's less than half the size by taking off 1 silly electron. And we see that's, roughly the same for all of these. Boron is even worse. It goes from 85 to 23. It's like it almost disappears. So we've lost the outermost electrons, and now we have a higher effective nuclear charge because we've changed some of the core electrons into the new valence electrons, so much smaller. Anions are much larger. And again, the larger part makes sense. You're adding an electron to the outside, makes it bigger. Not so intuitive is how much bigger it gets, and this is more difficult to explain. There is some shielding between the valence electrons, and so here when you're adding valence electrons, you might say, well, the core electrons are the same, the effective nuclear charge is the same. Well, actually, it's a little bit lower, and that's a detail we don't need to worry about too much. But again, here, it's roughly twice as big. So oxygen 73, the oxide ion 140 across. Then we get to isoelectronic ions. The prefix iso means the same. So iso, same. So same electron ions. These are ions that have the same number of electrons. They're not the same ion because they have different numbers of protons. But here's a table showing a series of isoelectronic ions. So here's sulfur. It has 16 protons. It forms a minus 2 ion by adding 2 electrons, so it's got 18 electrons. Chlorine has 17 protons, ends up with 18 electrons as a chloride ion. Potassium has 19 protons. It loses an electron, so it has 18 electrons. Calcium has 20 protons, originally 20 electrons, loses 2, so it has 18 electrons. All of these guys have the same number of electrons. They all have the same electrons as argon. Right? But the sizes are different. So adding electrons, making an anion, does it make it bigger or smaller? makes it bigger. And taking electrons away makes it smaller. And so when you take more electrons away, it gets even smaller. And so the trend here is this is the largest, 184 picometers, and this one's the smallest. So with isoelectronic, the trend is that it gets smaller with increasing number of protons. Smaller radius. I don't know what letter that was. Radius with more protons. The nice thing about these is they all have the same number of electrons. They all have those electrons arranged in exactly the same way. So the number of electrons is all the same. So then we're looking at the protons, and the calcium ion with 20 protons has to have a larger effective nuclear charge than sulfur. And so the greater nuclear charge is going to pull them in, and the radius will be smaller. So here, choose a larger atom or ion from each pair. Potassium atom or potassium ion? The atom, right? Because here we're looking at the same element, it's just atom versus ion. K plus is made by removing an electron, so removing makes it smaller, so then K is larger. Fluorine or fluoride? Fluoride is bigger. Because here the difference is we add an electron to fluorine. When you add stuff to the outside, it gets bigger. Ca2 plus or Cl minus? We don't really need a periodic table here, but we have one here. So if you do what we did with the other ones and find them on the periodic table, you're like, oh, I don't know. But then you have to recognize these both have the same number of electrons as argon. So then I'm looking at who has more positive charge in the nucleus. Well, the calcium does. It's 20 protons versus 17. So the calcium's going to be smaller because they get pulled in tighter, and the chloride's going to be larger. There are energy changes involved when an atom becomes an ion. So the ionization energy, abbreviated IE, is the energy needed to remove an electron from an atom or from an ion in the gas state. So in the gas state is like the small print. I'm not going to try to trick you with that. Ionization energy is always positive. So again, when you're talking about a positive energy, you have to think, well, what is the system that I'm talking about? The system is the atom. When I'm making this an ion, energy's got to come in to the ion, or to the atom to make the ion. I have to pay it for the electron. And we can write a chemical equation to describe this. Here we're using M to just represent a generic element. So there's M, the atom, and you add the ionization energy. You give it its the price there, you pay it, and then you've got a positive one cation, and the electron is now separate. So the electron has come out of the atom. This is labeled IE1. It's the first ionization energy. That's removing the first electron. Then you can remove a second electron, and a third, and a fourth, depending on how many it has. So the second ionization energy will be IE2. And now we're looking at an atom that's already lost one electron. So we're looking at the positive ion, and we're going to put energy into it again and take a second electron off, so now it has a +2 charge. The second ionization energy is always going to be higher than the first. Because it's like, well, I already sold you an electron, and now I've got, this increased positive charge, or, I've got the, I'm a cation, and I'm getting smaller, and so I've got this much higher attraction for my electrons, and so it's going to cost a lot more to get that second electron. There are trends for this, and they are related to the size. So here we have ionization energy in kilojoules per mole. That's how much you'd have to pay it for a mole of its electrons versus atomic number. And here we see that for the noble gases, the ionization energy decreases as you go down the group. And so let's think about, well, what's happening there? Well, as you go down the group, the atoms are getting larger and larger and larger. To remove an electron, you're taking it off the outside. You're pulling an electron off that's farther from the nucleus. It's easier to pick off. So ionization energy and size are inversely related. Large atom, smaller ionization energy. And this is where I think about taking 6 children to the big Fresno Fair, which I have never done. I've never taken all 6 of them because I wanted to have all 6 of them later that day. Fair seems like a really good place to lose children, right? But if you imagine, here I am, theoretically, with 6 children, and of course now, several of them are big enough that they would protect me from people, but, think back in the day. So here we've got helium. Helium has 2 electrons. Helium has 2 hands, right? So here's a mom with 2 kids, and she's got a death grip on those kids, and she's going around, and it's going to be really, really tough to take one of those kids, because she's literally holding on to them, right? And here am I, and I've got 2 hands also. I think you should grow an extra arm every time you have a child, but then that would make shopping even more difficult. Holding on to 2 and saying to this one, no, you hold on to your brother, you hold on to your brother, but I can't hold on to all of them. It'd be so much easier to take one of my children, right? I like these as like really out there analogies because it's just like easy to remember. Right? So here's xenon. Xenon's big atom. Easier to take an electron off the outside. Lower ionization energy. Lithium, sodium, potassium, rubidium. The trend there is the line there is not as steep. The slope isn't as steep. The change isn't as much, but the trend is still there. As we go across a period, what happens to the size? Gets smaller. So what do you think happens to the ionization energy? It goes up because it's harder to take an electron from a tight, small atom. So as we go across a period from lithium to neon, we see a general trend of increasing, but there are a couple of blips in there. And then the transition elements, again, they're roughly the same size, and so their ionization energies are very, very similar. So this is one of those 3D bar graphs, or I really do need to look that up. Here we see as we're going across, the ionization energy increases in general, and if we're going down a group, it decreases. So this trend is exactly the opposite of atomic size. Predict.
But because of size.
Yes, but because of size. So, you could rote memorize the size trend and then rote memorize that this is opposite. But I think it's a lot better if you can rationalize why, if you can explain it to yourself. So tin or iodine, we're looking for the higher first ionization energy. So again, we're going to find these in the periodic table. There's tin, and here's iodine. Higher ionization energy, is that going to be the smaller or the larger? The smaller, because it's harder to take an electron away. So I'm looking for the smaller atom. The trend is I'm going across from tin to iodine. Are they getting smaller or bigger? They're getting smaller. So we predict that iodine has the larger first ionization energy. There will be problems like this in the exam. Calcium or strontium? Again, we've got to find them. Here's calcium, and here's strontium. higher ionization energy, I'm looking for the smaller atom, right? So who's smaller, calcium or strontium? Calcium. Carbon or phosphorus? Here's carbon. Here's phosphorus. Again, I'm looking for the higher ionization energy. I'm looking for the smaller element. This is a diagonal, so then it's possible that we can't tell. So the trend going across would predict that phosphorus is smaller. The trend going down predicts that carbon's smaller. So we're going to say can't tell. Can't tell based on trends alone. And then fluorine or sulfur. So here we have fluorine, and here we have sulfur. And again, this is a diagonal, but it's the diagonal the other way. So the trend is as we're going across, they get smaller. That predicts that fluorine is smaller. When we go down, they get bigger, so that predicts that fluorine is smaller. So fluorine's smaller, so fluorine has the higher ionization energy. Yeah. There's so many places that you can get it backwards, so you really just kind of have to spell it out for yourself. And then, write it down, and then, on an exam you can come back and read through it, and you're like, yep, okay, good. Yeah, it's confusing. Exceptions. Of course, there are going to be exceptions, right? I'm more interested here in peeking into the meaning of these exceptions. So generally, we see the first ionization energy increase as we go from left to right across the period because the atoms are getting smaller. But we see an exception between group 2A and group 3A. Boron has a smaller ionization energy than beryllium, even though it has a larger radius. So what's going on there? Well, it has to do with the electron that's being lost. What orbital is it in? So we need to look at the orbital diagrams for these two elements so that we can get an idea of what's going on here. So for boron, and we're just going to look at the valence. So there's 2s and 2p. And for beryllium, I'm going to look at, we'll just draw the same boxes. 2s and 2p. How many valence electrons does boron have? What group is it in? 3. So 1, 2, 3. And beryllium has how many? Just 2, right? So when I'm removing an electron, I'm removing a valence electron, and these are main group elements, it's reverse order of filling, right? So the one I'm removing, I'm removing this one from beryllium, and I'm removing this one from boron. The 2p sublevel is a little higher in energy than the 2s. So taking an electron out of the 2p doesn't cost quite as much as taking it out of the 2s. Does that make sense? This sublevel is at a higher energy. That's what it filled after the s. And so here I'm removing an electron from this higher level, and here I'm removing from a slightly lower level. The 2p orbitals in general are a little bit larger than the 2s, if that helps, and so it's a little bit further away, and so it's going to be a little easier to remove than this 2s. We also see an exception between groups 5A and 6A, between nitrogen and oxygen, and here we've got it all drawn out for us. So removing an electron from nitrogen, we're going to remove this one. Removing one from oxygen, reverse order of filling, it would be this upside down one that's paired in that first orbital. This one has to pair up, and so it's easier to get rid of that one than it is to get rid of this one, which is pretty happy there with his own bed. We also have this effect of this is a half-filled orbital, and that's like a bonus situation. You get a coupon at the hotel if you can half-fill a room, right? So here we've got a half-filled room, and by removing an electron, we're going to mess it up. Here, by removing this electron, we're going to get a half-filled room. So we would expect that oxygen being slightly smaller would be harder to ionize, and yet it's actually easier to ionize. And I am not going to test you on that, but I think it's helpful that we can use quantum mechanics and look at the electron structure and get an idea of why that might be. There are reasons behind these things that we see.
Are these exceptions true for everything down the group?
They're pretty much true for everything, yeah. But again, I'm not going to grill you on them, so we're not going to, because if we look too far, then if we look too deeply, it gets messier and messier. So we're going to stay up here where oh yeah, here's a trend. This one I think is easier to understand. So you remove one electron, you got to pay for it, right? You remove the second electron, you're going to have to pay more. And a third one is going to cost even more. So each one that you remove is going to have a higher ionization energy. That makes sense. What's interesting, though, is that we see this huge jump. So for sodium, the first one's around 500, and the second one's like 4,500 to remove. Whereas with magnesium, the first one is, a little over 700, and then the second one is 1,400. That's just only about double, right? And this is almost 10 times as much. Shouldn't there be kind of a rough pattern there? Well, for sodium, when you remove the first electron, that's the one valence electron. When you remove the second electron, now you're messing with the sodium ion that's got its noble gas configuration, and it's strutting it because I look like a noble gas. I'm cool. And so to take an electron away, you're going to mess that up, and that's really not energetically favorable. You're going to have to pay a lot for that one. For magnesium, you take one electron off, and he's like, yeah, okay. I'm still not great because, I still have this, I lost the scarf, but I've still got the hat that my mom made me wear. And so, the second one, you got to pay to take that off. But once you've taken off 2 electrons from magnesium, now he's got that electron configuration of a noble gas. It's kind of where he wants to be, right? It's a sweet spot. And so then to take a third one off and mess that up, it jumps way up. Yeah, it's messing up the 8. You got to pay, and there's an increase in cost for each one to get to the 8. But once you've got the 8, then the price goes way up to mess it up. So we look at a table like this, which is, probably a bit difficult to look at, but what we're seeing here is successive ionization energies, so the first, second, third, fourth, fifth, sixth, seventh, and looking at the different elements. And so for sodium, you take the first one off, that's a valence electron. The second one, you're getting into a core electron, the price jumps. Magnesium, you take the first one off, the second one. The third one is where you're getting into core electrons. Aluminum, 1, 2, 3, and then there's the fourth one that jumps way up. And so we see this consistent jump in ionization energy when you go from removing a valence electron to removing one of the core electrons.